So yeah, hi, my name is Cyrill Miksch, and I'm also from the University of Vienna, where I write a bachelor thesis on neural rendering for subsurface scattering. The goal is to approximate the transmission part of a real-time rendering solution for subsurface scattering and see whether a neural shader can improve upon the performance while still keeping the visual quality. And furthermore, I want to see how different feature sets, network architecture, and sample count factor into performance and visual fidelity. How do I do that? I expanded upon an already existing renderer and added a data collection pipeline, trained a neural network, and implemented an inference as an alternative render path. Uh, After that, I evaluated the results. But first of all, what is subsurface scattering? Basically, it's light transport inside objects, which is especially important if you want to render material like skin or foliage, marble or wax. That is material that is emanating like a soft color bleeding, like partially translucent material. Um, this concept has been tackled for some while now, first in offline rendering, then in real-time solutions. And the project or the solution I'm working on, or my project is building upon, is the NVIDIA RTX character renderer, which is open source on GitHub. And it has an implementation of a real-time rendering surface scattering solution by Zhang and Dion. That's the one half of the project. The other half is neural rendering, that is neural networks, that is multi-layered perceptrons, as they have been envisioned in already in the 50s, and especially the ability to approximate mathematical functions arbitrarily well, which have been proven in different degrees over the years, is especially promising for this employment. In graphics programming, it has been used mostly, or like first or most prominently, one could say, in upscaling and denoising, for example, DLSS. And in recent times, I mean, like very most recent, like the last years, uh, more and more parts of the rendering pipeline have been substituted by neural networks, or at least try to substitute those parts, be it neural shaders, neural materials, or neural textures. I have the sources on the last slide. Let's look into the NVIDIA RTX character renderer, which I've already talked about. It implements the solution by Zhang, which basically combines two different approaches to subsurface scattering. It combines a diffusion profile and a ray trace part. And this ray trace part also has two different parts. One is a so-called boundary term, which basically is evaluating the light as if it would travel unscattered through the volume. And the other one, the other part is the scattering term. And that is sampling a position on the way through the body and sampling a direction and evaluating the scattered ray. And in my project, I only try to approximate the second part of the second part, so to say. That is just what I said, the last, like um, the scattered ray evaluation. On the right side, you see the uh, the renderer, and we will see more of it soon. Uh, just a quick overview of over what I've did. I mean, first I constructed a feature set. That is, I used the parameters which also govern the analytic solution, like material parameters, volume geometry, ray tracing geometry, but then turned it into a suitable form for neural networks. For example, taking the logarithm, so to keep the variance in check, or taking the dot product of two vectors instead of all two vectors and all their parts. But I also tried alternative reduced feature sets which don't follow those guidelines actually, and those and try to minimize redundancy in the feature set, which I thought when thinking of universal approximators, one wouldn't put into a function parameters which you can even calculate inside the function out of the rest of the parameters. That's redundant. And if the function can do it, why shouldn't the neural network? And this actually proved pretty good, pretty successful. Like just some days ago, I will show the results shortly. Yeah, then I created a data pipeline in the renderer. It uses a special interface by NVIDIA, which is kind of, I mean, one has to get into that as well. It's API agnostic, but leans more towards DirectX, as I can tell. And I mean, it's in C++ and HLSL as shading language. Usually Slang is preferred when it comes to neural rendering, but the character renderer uses HLSL, so I stick to that. And in the end, it doesn't matter that much syntactically. Yeah, I stored the feature set in a sample struct, wrote it into a buffer, copied the buffer, read it in the CPU, and then wrote the data into a CSV file, which I then used to train different networks in Python using PyTorch library, like the standard way. Different network architectures. I started with a rather small to medium-sized network with 2 hidden layers, then tried a bigger one, a tiny one, and then one with this before mentioned reduced feature set. And I also did try different sample sizes. I first trained only on 3.6 million samples, which I thought would be already enough, but it turns out the results improve a lot by increasing the sample size. Yeah, I use Atom Optimizer, mean squared loss as a loss function, and ReLU activation function. That's all very basic setup when it comes to neural networks. Then I built an inference path on the C++ HLSL side, meaning I reconstructed the neural networks there. I stored the weights in just regular C-style arrays, and to be able to calculate to run the networks inside the renderer. And then I implemented some add-ons for the UI so that I can switch between different architectures, and also to collect the data. I used an UI element. Here you can see like a short source code example of this kind of translation or transfer between Python, the Python side, and the renderer side. Like on the left side, you see in the upper left the neural network, and it becomes like, for example, the ReLU activation function basically is just the max function, and on the downside, like on the lower part, you see yeah, the tensor weights in Python, and I mean in the Jupyter Lab notebook, which runs Python, and on the right side the C-style arrays. Let's go into the evaluation. I mean, by the way, I have to apologize. The translation to the after uploading the slides, it got a bit mixed. Like the layout is a bit shaky, but I hope you can see it nonetheless. Yeah, the evaluation, it uses a scattering sample count of 8. On the far left, you see transmittance not enabled, like no transmittance. That means no light is hitting the ear from the back and using the translucency to emanate through the ear. Yeah, and the next one is the analytic solution, like which I use as the ground truth to compare against. That's why I put this green rectangle around it. And the FPS, like it's varying kind of like ±4 even, but I used to take some a bit higher range, one of the higher in the higher parameters. The next one is like the first try I did with the neural network with only 3.6 million samples. It was rather noisy. You can see it that well on the slides. It's just dark, but actually there was a lot of fluctuation. The next try was to make it bigger, which worked very well, very stable, a bit overshooting, a bit too bright. But the biggest problem was that the performance was very bad. Like it's only half as fast as the analytic solution, and that doesn't make sense then. And the next one was really also very stable. It's the smallish network again, but with 10 million samples more. And this resulted in a very stable image and mostly not distinguishable from the analytic solution, I'd say. However, what I thought is scattering sample count of 8, meaning you're taking 8 samples for each BSDF sample and averaging on the scattering evaluation. And that's actually rather high, at least for this year. And I thought it might be good for 8 samples, but it would be better if it worked also for smaller samples. And so it should be much faster. And so I tried a very tiny network, increased the sample size. And this, on the slide, it looks good, but actually it has some flickering and flash effects, which you will see in the video showcase in a short while. So this doesn't work out as well. But this aforementioned reduced feature set network worked very well. I thought not as stable as the version before, but in the video you also see no difference, I'd say. And it's even faster. So with these numbers on the slides, it's 34% more or less. When I first evaluated it, it was already even 40% faster. So let's have a short video showcase. I uploaded a video. So first the transmission part is off. And when we enable it, like on the left, you see like in the ear how the light goes through. That's the analytic solution. You see how if you change the light, like the visuals are different. You have 54 FPS. You see the frame rate on the upper left. Now this is the stable version, like the small to medium sized network, which I think which is like very comparable, which is not the case for the tiny one, which when you look at the eye, you see like these little flashes of light, even in parts which shouldn't matter that much. So this didn't work out as well. But this one with the reduced feature set, it improves a lot on the frame rate, and it's as stable as the other solution. And yeah, if you turn it off and on again, so here I have to run more tests, but at least up until now, you don't see much of a difference. Okay, so to conclude, performance gains were from 10 to 40% while keeping visual fidelity. I've already talked about the different networks and how they change. Like the larger network was lacking in performance. And especially the reduced feature set, which I rather recently tried, was very well and resulted in big gains with only minor visual loss. I mean, right now I don't see that much loss at all. And it's even faster already for 2 scattering samples. So I trained it on 8, having the good visual quality, but running faster. Of course, there are additional optimization possibilities. One could think about the attention architecture, for example. That might be a bit too much for this topic, but yeah. So thank you very much for your attention.
Thank you. That was interesting, and we are going to go to the next presentation.